Welcome to Spring LIB.
Everyone, today we're doing chapter 11, problem 58, and this problem asks us to use this acetylene starting material or an ethyl oxide and any alkyl halide, so that's just hydrocarbon X, so we can just do arbitrarily a CH something X as starting materials for the generation of these four products. So let's start with A. So A, we have your alkyne bond, but then we add 1, 2, 3, 4, 5, 6 more carbons. So 1, 2, 3, 4, 5, 6 carbons. So how do we do that? Well, we can make the acetylene from previous problems, such as 56. We make acetylene into a nucleophile by deprotonating it, and we add this alkyl halide with the appropriate number of carbons. So we already have these two carbons here from our starting material. We have these two carbons here from the starting material. So we need 1, 2, 3, 4, 5. Should be 6. 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6. Yeah, 1, 2, 3, 4, 5, 6. So we know if we start with acetylene and deprotonating it using sodium hydride, we will get your one side of it will get deprotonated to form our carbanion, which would, if you react it with an electrophilic alkyl halide with appropriate number of carbons that we're trying to add, so 1, 2, 3, 4, 5, 6, with the halide being bromine or chlorine, and we can get a nucleophilic attack to get our final product being 1, 2, 3, 4, 5, 6 carbon substituent, which is product A. Now let's do B. So B, we're doing the same thing as A. We're adding 1, 2, 3, 4, 5, 6 carbons to one side, but in addition, from this step, now we're adding 2 more carbons on the other side. So it's very similar to problem 56, actually, what we just did. So this is A, so in B, so let's add carbons for on one side first. It doesn't actually matter from which side you add it on. It doesn't have to be the longest or shortest side, just any side, as long as it's sequential order. You sequentially add them on. So let's just, for the sake of this problem, let's first add the 6-sided one, because we already know how we do that. So 1, 2, 3, 4, 5, 6 with the halide, and actually this time I'll use chlorine just to emphasize that you can use any halide. 1, 2, 3, 4, 5, 6. But now from this step, we need to deprotonate the other side of this acetylene. We need to take away this proton to make a carbanion on this location. And then we can add our now 2 carbon source electrophile. So 1, 2 with any halide, and we'll use iodine in this case. So 1, 2, 3. 1, 2, 3, 4, 5, 6. 1, 2. And this is your product B. So now let's see for C. So C, what do we have? So we have actually 1, 2, 3, 4, 5, 6. So once again, you're adding that same 6 carbon to one side of this alkyne, but then you're adding 1, 2, and an alcohol. So it seems, so if you guys see that we're adding 2 and an alcohol, but what we can use is any alkyl halide. So some may say that, oh, well, once we get this product here, we can deprotonate the other side of this alkyne, and then we can add 2 carbons that we need, and then one side will be a halide and the other side will be an alcohol, and then you'll just get your 2 carbons and alcohol product because your halide will get kicked off. Well, we have a restriction for starting materials. It can only be an alkyl halide. This is not an alkyl halide. We have an alcohol here. So let's see what other starting materials we can use. Well, we have 2 carbons in this ethylene oxide, and we have an oxygen. So this also provides a right number of oxygens and carbons, and this acts as electrophilic. These 2 carbons act as electrophilic carbons because of the electron pulling density of oxygen. So it's pulling electron density away from these carbons, making these electron poor and electrophilic, susceptible to nucleophilic attack from your acetylene or from your alkyne carbanion nucleophile. So for C, let's do the same thing. So for C, we're taking acetylene and we're adding 6 carbons to it to make that one side. 1, 2, 3, 4, 5, 6. Cl. 1, 2, 3, 4, 5, 6. But now we're going to add sodium hydride to make a carbanion. But then our electrophile this time is going to be this this ethylene oxide, and that will form, so your carbon ion, after this deprotonates it, with a carbon ion that can attack either side, making a bond. You make a bond, you break a bond, so this pops open. So then you'll be left with an O minus, but we need an OH. So how do you neutralize O minus? Well, in the past, we've used just added water as well. So if you add water, then you'll have an alcohol at the very end and no charges left. So you have your 1, 2 carbon, and then your OH. So this is for C, and then for D, what do we have? So for D, we are having 1, 2, 3, 4, 5, 6 carbons, just like in all the other examples. And then we're having 2 carbon oxygen, just like in C. But then from the oxygen step, we're adding 2 extra carbons. So now oxygen needs to act as a nucleophile. So if I deprotonate this oxygen, I'll get O minus, which would be a charged electron-rich nucleophile, which can attack some sort of alkyl halide. So for D, let me write this in red. So for D, we actually need to redo all these steps of C to get to this point, because we add our 6 carbons to our acetylene, then we deprotonate it and add the ethylene oxide to get this alcohol. So now we're at this step. But now we need to deprotonate this alcohol with any deprotonating agent like sodium hydride or an amide, NH2 minus, and then we'll get an O minus nucleophile, and then we need to attack an electrophile. So we need a 2 carbon electrophile, so 1, 2 carbon, and we need a leaving group, so it can be any halide, so we'll just say bromine, and then we'll get an SN2 nucleophilic attack with this O, and now there's 2 carbons. So then we get our product D from C.